So we're going to look at examples 7, 8, and 9 from the notes from yesterday. So we're following the same processes that we were doing yesterday, where we're going to be doing primarily U substitutions. But the biggest difference between what we were doing yesterday and what we're looking at today is the fact that the ones we're looking at today have bounds. So notice that the ones from yesterday, right, were just general antiderivatives. There was no from A to B, whereas these ones are going from a specific value to a specific value. So this adds a layer to how we can evaluate these integrals. So what we're going to do is when we do a U substitution with these types of problems, we're also going to have to change our bounds. So right now, the bounds here are x is equal to pi and x is equal to 0, right? Because this integral is in terms of x. So when we change to using u and we rewrite our integral with our u and our du, we are going to also have to change our bounds so that our bounds are in terms of u as well. Okay, so what we'll do first is figure out what u is going to be. So in this case, u is going to be that inner function. And so u is going to be x plus pi over 2. Taking the derivative of that, that gives me du dx is equal to 1. And then multiplying by my dx, I get du is equal to dx. So then I'm going to substitute that in here. So I have the integral of sine of u du, and now I have to change my bounds. So changing my bounds is going to be done based off of our u substitution equation. So you see that it tells us that u is equal to x plus pi over 2. Well, if our x is pi and our x is 0, that's what we're going to use to determine our new bounds in terms of u. So our first bound is that x equals pi. So u is equal to pi plus pi over 2, which means that that first bound would be 3 pi over 2. And then x equals 0 is our other bound, so that means we would have u is equal to 0 plus pi over 2, so our other bound is pi over 2. So then I'm going to plug those back into my integral. My u integral is going from pi over 2 to 3 pi over 2. And then we can anti-differentiate this. So the antiderivative of sine is cosine, but it would be negative cosine, right? Because the derivative of cosine is negative sine, so the derivative of negative cosine would be positive sine. And then we're going to evaluate this from u equals pi over 2 to u equals 3 pi over 2. Because we have changed our bounds to be in terms of u, we don't have to go back and plug back in our x's, because all we're going to end up doing is evaluating this anyway. So we can actually evaluate it while it's in this u form. So we have cosine of, that'd be that 3 pi over 2, so negative cosine 3 pi over 2 minus negative cosine of pi over 2. And so remember our unit circle. At pi over 2, the x-coordinate is 0. And at 3 pi over 2, the x-coordinate is 0. So this gives me negative 0 plus 0, which is 0. These ones with the bounds are good ones for you guys to check on your calculator, especially with the homework and on your quizzes or tests, because you can just type this in and see if you get the right result. You don't have to do the u substitution into your calculator, but you should get the same answer from the original x form to the very end if you've done everything correctly. Okay, so it's a good way to check yourself as you go. Okay, so looking at number 8, we're going to do kind of the same thing here. So we want to do a u substitution here. I'm going to make my denominator function equal to u because that has the higher exponent. And when I take the derivative of that, du dt, that gives me 2t. So then solving that for dt gives me du over 2t is equal to dt. And so I'm going to substitute that in. Remember that my bounds here are in terms of my original variable, which in this case was t. So I have t equals 4 and t equals 0 as my bounds. So I'm going to write my integral. This is going to be t over u times du over 2t. I'm going to change my bounds. So remember to change your bounds. You're going to use the u equation that you have here. So we know u is equal to 2 plus t squared. My two different bounds are 4 and 0. So if t is equal to 4, that means u is equal to 2 plus 4 squared. So u would be equal to, that'd be 18. And if t is 0, then that should give us u is equal to 2. So our new bounds are going to go from u is equal to 2 to u is equal to 18. And then now I'm going to do my rewriting here. So my t in my numerator divides with this t in the denominator. I'm going to take the 1/2 out of my integral. So this gives me 1/2 times the integral from 2 to 18 of 1 over u du. Remember that it's easier for me to write this as 1 over u du as opposed to writing it as du over u for the purposes of seeing how we're going to antidifferentiate this. So remember that the antiderivative of 1 over u is the natural log of the absolute value of u. So we have 1/2, and then it's going to be times that antiderivative, so natural log of the absolute value of u, but we're evaluating that from u equals 2 to u equals 18. So that means I'm going to have 1/2 times, that would be the natural log of the absolute value of 18 minus the natural log of the absolute value of 2. And so you could, in theory, leave your answer like this. That would be fine. There are a few ways that you could simplify this, though, using our properties of logs. And so if this were a multiple choice question, you might have to continue to simplify. And so I'm going to go through how you would simplify this further. But know that if this was like a show your work question, this would be a perfectly acceptable final answer. Okay. So remember that with our properties of logs, that you can combine logs that are separated by subtraction by using division inside of your log. So this would be 1/2 times the natural log of absolute value of 18 is just 18, and absolute value of 2 is just 2. So when I combine these using division, I get the natural log of 18 over 2, which is 9. So I have the natural log of 9. And then remember also that with logs, you have this property that your exponent can be pulled down in front of your log. So here I could pull this number from in front of my log up as an exponent, so that this would be the natural log of 9 to the 1/2. And 9 to the 1/2 is like the square root of 9. So that could give me the natural log of 3. So that would be like your most simplified possible answer there. This, though, here is also, like I said, a perfectly acceptable final answer if we are doing a show your work problem. If it's multiple choice, it might give you one or the other as a possible option, but both would not be there. So you would have to simplify that original answer to get to your natural log of 3. So then for number 9, we are going to, again, make a u substitution. So our u is going to be an inner function here. And so we have two functions. We have the 3x squared, and then we have the e to the x to the third. The one that's the inner function is the x to the third. So that's going to be my u here. U is going to be x to the third. So taking my derivative, that gives me 3x squared. And then solving this equation for dx gives me du over 3x squared is equal to dx. And so then we're going to go ahead and plug that in for dx here. Our bounds, remember, are currently in terms of x, so we're going to have to change those. So substituting my u's into my integral, I have 3x squared e to the u times du over 3x squared. So that's where I'm at right now. And then I'm going to change my bounds. So changing my bounds. Changing the bounds. Again, remember that we have the equation that we're going to use to help us change those bounds right here. Our u is equal to x cubed. So my x's that I have as my bounds are x equals 5 and x equals -1. So if u is equal to x to the third, then that would be u is equal to 5 to the third, which would be 125. And then for our other bound, that would be -1 to the third, which is -1. So my bounds here are going from u is -1 to u is 125. And then now I'm going to simplify that integral a little bit. So I have the 3x squared e to the u, and then the du over 3x squared. The 3 and the x squared divide with this 3 and x squared. And so that gives me the integral from u equals -1 to u equals 125 of e to the u du. And remember, your antiderivative of e to the u is just e to the u. So this is e to the u evaluated from -1 to 125. And so plugging those in, I have e to the 125 minus e to the -1. And you can't really simplify those because you're subtracting. And so you can't combine your exponents like you would if you were multiplying here or dividing here. So this is giving us something that is a bit different from what we have seen typically, right? It gives us the integral, but notice that inside of that integral, it says f prime, right? So it's not giving us that actual outer function. It's just giving us our inner function, which is cosine, and then this additional function, which is sine. And in the directions, it says that f of 0 is 5 and f of 1 is 7. So what we're going to do is go through this and make our u substitution and kind of work through this process, changing our bounds, doing things the way that we had done. And I think you'll see how this ends up working out pretty nicely. So our u is going to be our inner function. So our inner function in this case is this cosine, because that cosine is being plugged into whatever f prime of x is. We don't know what f prime of x is, but whatever it is, cosine's being plugged into it. So u is going to be that inner function, cosine of x. And then I'm going to take my derivative. So du dx is equal to derivative of cosine is -6 sine. And then solving this equation for dx is going to give me du over negative sine of x is equal to dx. So I'm going to plug that in for my dx in my integral. So that's right here. So I have then sine of x times f prime of u times du over negative sine of x. So I'm going to change my bounds. So right now the bounds are x equals 0 and x equals pi over 2. So I'm going to change those bounds, so that I have from my equation here, right, u is equal to cosine of x. My bounds are x equals pi over 2 and x equals 0. So if x is pi over 2, that means u is equal to the cosine of pi over 2. And if we look at our unit circle at pi over 2, the x coordinate is 0. So that is 0. And then here we have if x is 0, u would be equal to the cosine of 1, cosine of 0, which is 1. Over here on our unit circle, the x coordinate is 1. So changing my bounds then, I have that this is going to go from u equals 1 to u equals 0. I'm going to rewrite this a little bit. My sine here divides with my sine here, and I'm going to pull that negative that's in that denominator out in front of my integral. So I have negative integral from u equals 1 to u equals 0 of f prime of u du. Now, notice that my bounds are in the incorrect order, right? This is going from 1 to 0, should be going from 0 to 1. So I'm going to reverse my bounds and pull a negative out. So then I have negative integral. So that would be positive integral from u equals 0 to u equals 1 of f prime of u du. And then now at this point, we're using the FTC. The antiderivative here, this integral, remember that that's going to equal f of 1 minus f of 0, f of b minus f of a. That is the FTC. Right? And so then here, f of 1, going back to the instructions, f of 1 was 7, and f of 0 is 5. So plugging those in, that gives me 7 minus 5, which is 2. So just like we have been doing, we're going to make a u substitution. And this one doesn't have any like f primes or g primes or anything weird. So this one should be a pretty straightforward u substitution, change our bounds problem. So u is going to equal t plus 2. And taking my derivative, that gives me du dt is equal to 1. So du is equal to dt. And so I'm going to go ahead and plug that in here for my dt. That gives me then the integral of 1 over u du. And I have to change my bounds because right now my bounds are in terms of t. So I'm going to use this equation. I have for my upper bound, t is equal to e minus 2. And for my lower bound, t is equal to negative 1. So using my equation, u is equal to t plus 2, that would mean that u is equal to e. And then for my other bound, t plus 2, that'd be -1 plus 2, which is 1. So my bounds here are going to be from u equals 1 to u equals e. And so anti-differentiating this, the antiderivative of 1 over u, remember, is the natural log of the absolute value of u. And we're going to evaluate that from u equals 1 to u equals e. And so just plugging those in, that gives me the natural log of the absolute value of e minus the natural log of the absolute value of 1. Natural log of e, absolute value of e is just e. Natural log of e is 1. And then natural log of 1 is 0. So this simplifies to just 1. Here, this one does not have bounds. It just says find an antiderivative. So here, you don't necessarily have to put a plus c. I generally still put a plus c even when it says to just find an antiderivative, because I feel like you're more likely to forget to put the plus c when you need to if you don't. But it's technically not necessary here. So this one has kind of that strange notation of like the g primes are in here with these other functions, these g of x's. And so I'm going to make my inner function, so this 1 plus g of x that's beneath this square root, I'm going to make that my u. So 1 plus g of x is u. And then taking the derivative of that, derivative of 1 is 0. Derivative of g of x would be g prime of x. And then multiplying by my dx on both sides and dividing then by my g prime to find what to find what dx is, I get that dx is equal to du over g prime of x. And so if I plug that in, I have g prime times the square root of u times du over g prime of x. And notice that this g prime of x divides with this g prime of x, giving us just the integral of the square root of u du. And remember that it's much easier to anti-differentiate that square root of u if you write it as u to the 1/2, because when you have it written like that, you can use the reverse of your power rule, adding 1 to your exponent and then dividing by that new exponent, which would then give you 2/3 u to the 3 over 2. Now, with the ones that we were just doing, because we were evaluating them, we didn't have to go back and plug in our x's, right? Because we were changing the bounds, and then we plugged in our bounds and we actually found the numerical value for the antiderivative. Here, there are no bounds for us to actually evaluate this at, so we are going to go ahead and plug back in what we had for u. So u was 1 plus g of x, and so I'm going to plug that back in here. So that'd be 2/3 times 1 plus g of x raised to the 3 over 2. And then we can put our plus c. Although the plus c, like I said at the beginning, is not necessary, but it is, I like to put the plus c.